All right, so welcome back. We are talking about worksheet 5.1, number 1. That's what I assigned yesterday. It was a really tough one on there. It was number 5. And to be able to explain number 5, first of all, I got to make sure you understand two important base skills. And I remember how I did that top 20 thing, and I made you learn all those 20 things because I knew they would really help you later. And some of you guys took the opportunity and did learn all those things, so you're in a much better place now. Because one of those things was, for instance, finding common denominators. You have to be able to handle common denominators to be able to handle this harder trig stuff. Because you're going to be adding fractions together, and to be able to add fractions together, they have to have a common denominator. All right, so there's another skill you have to know, and that's factoring. And you might not even think of it this way, but if you have sine x, cosine x, plus sine x, do you get that they both have a sine x in them? If they both have a sine x in them, go ahead and factor it out and tell me what you have left. Write it down on your notes. This is not, don't write in the beautiful sheet that you made of your list of identities. We'll save that to be special and pure, and we'll add to that only as you learn new identities. But this is just a blank piece of paper for your notes. So once sine gets factored out, what you got left? Sine x comes out, and you got what left? Come on now. Cosine x, what? Plus 1. Because when you're factoring something out, what's really happening is you are dividing by that thing. And do you get how when I divide by sine of x, this one would cancel out, and then you'd have cosine left. And these two would both cancel out, and so you'd have a 1 left. Because really, when they cancel, they turn into 1s. Okay, do you get that one? Why would that ever matter? Because here is a typical question. And it looks really, really complicated, but if you understand what I just told you seconds ago, as soon as you get that top factored, good things happen. Try it. Some of you are not writing yet. I know you may be tired. Snap out of it so I can keep you in here. The sine x cancels, or sorry, not cancels, factors out when I have cosine x plus 1. All right, so I factored out the sine x, and then on the bottom, I still have a cosine x plus 1. And why is that good? Because these cancel. So the answer is just sine x, see? Did you understand how that factoring worked? I'm going to give you another one. See if you can factor this. 1, no, wait. Sine x plus tangent x. Factor something out of that. You have to be able to go above and beyond to do this. It's not quite as simple as last time, is it? Give you a hint. Replace the tangent x with something else. Then factor something out. Replace tangent first. Sine x plus, what's tangent we replaced with? Sine x over cosine x. That's what tangent is, sine over cosine. Now do you see that there's a sine in both of them and therefore can be factored out? Sine comes out, and what do I have left? 1 plus, not just cosine. When I'm factoring, what am I really doing? I'm dividing by sine x, dividing by sine x. And what happens here is sine x over sine x. That part, do you get how that equals 1? Okay? And this other part, when I divide by sine x, that cancels and that cancels. When something cancels, what does it leave behind? A 1. And therefore, it's 1 over cosine x. What's 1 over cosine equal to? Secant. There's your answer. do another one like that. Cosine x plus cotangent x. Factor something out of that. Well, the cotangent is not sine over cosine, it is cosine over sine. In case you didn't know that, you'd probably be stuck, but now maybe once I write it this way, you'll see what to do. Do you get that these both have a cosine in them? So, factor out the cosine. And you'd have what left? What that really is dividing by cosine. Dividing by cosine. These turn into a 1 plus those cancel, and what do you have left? 1 over sine, but that's also known as cosecant. CSC. There we go. And why would you ever need that? Because probably on the bottom of the problem there would have been a 1 plus cosecant. That way the 1 plus cosecant could cancel. Yes, sir. I know how to do 18, but I'm not willing right now. Yes. Okay. All right. I do want to help you with number 5, though, and now's a good time to do number 5 because you've just learned how to do it. You can factor stuff out. So let's look at number 5 now with new eyes. Not like in Minority Report, Tom Cruise, where he actually takes somebody's eyes. He doesn't take them. He buys them on the black market because they took his eyes out. So he gets new eyes on the black market and puts them in. And then he can use a retinal scanner now for somebody else because he doesn't have his own eyes anymore. He has like Mr. Nakamura's eyes. Anyway, it's a good movie called Minority Report. So looking at this with new eyes, it could mean something completely different if you were talking like that. All right, a little random, I know. Sine x plus tangent x is on top. That's the part that you can do the factoring little deal with. Try it. And if you do it right, you'll get a 1 plus secant. And that way they'll cancel on the bottom and the top. Now, not many people take me up on this, but I'm telling you, it really is true. You can do so much better. These are so much easier if you have lots of room to write. I do math tutoring outside school, and I get whole sheets of paper. I use the ones that are recycled paper, and I take whole sheets of paper. For almost every problem I do, I use an entire sheet of paper for it. Okay? Because it's already recycled paper. And then I recycle the recycled paper, and it probably turns into toilet paper somewhere. So somebody's probably wiping with math problems as we speak. Anyway, I encourage you to take plenty of paper as you're doing your problems. Like if you're doing number 5, I wouldn't be trying to squeeze it in there if it's a hard one. I would go off on a separate sheet of paper, and I would fill up a whole page. Be proud of the fact that you're going to do really complicated stuff that takes a whole page to do. You weren't able to do this until now. All right. So the sine x plus tangent, I'm going to break. I got a tip for you in general. In general, you want to move towards getting everything into sines and cosines. You don't have to do it, and it doesn't work on every problem, but it's a general rule. So if I want to generally move towards sines and cosines, what should I change tangent into? Sine over cosine. So on the top, I'm going to now have sine x plus sine x over cosine x. And now do you see you can factor something? They both have a sine in them. I'm only doing the top right now. I'm totally ignoring the bottom part here. I can look at that later. I'm still finishing the top. I'm factoring out the sine x, and what do I have left? 1 plus 1 over cosine, which is really what? Secant. Now I'm going to bring that denominator from up here, I'm going to bring that back again, and it was 1 plus secant x, and that cancels that. And I'm down to just sine. And it'd be really sad, kids do all this work and then I have to mark it wrong, because why? Yes, you have to finish the deal, which is if a proof, you have to finish your proof statement. On the other side is a sine x that came all the way down. So sine x equals sine x. Okay, I'm just keep pounding that in because I want to make sure you don't make that mistake on the test. Yes? If you even have one last step left, like if you said instead of sine x, that is the same exact thing as 1 over cosecant x, that is what sine x is, but see, it's not finished. It has to be identical. So even though this is a true statement here, you can't leave it like that. You'd have to finish with sine x equals sine x. Okay, so we just did number 5. Now there's another skill. That was with factoring. There's another skill you need, and that's common denominators. So let's talk about common denominators. First, let's talk about the easiest kind. Let's say you had 1/2 plus 3/5. Obviously, they don't have a common denominator. What would be a good common denominator? 10. So what you do is you ask yourself, what could I do to this fraction to make it into tenths? I should multiply by 5 over 5. If I just multiply by 5 on the bottom, that's not fair. I got to do it to the top and bottom. Because multiplying by 1 like this is okay. And then over here, I'm going to multiply by 2 over 2. And now do you get I have a common denominator of 10. Now what do? I take these two denominators of 10 and do I add them together and make 20? No, that wouldn't make any sense. The answer is in tenths. I just have one of those common denominators on the bottom. And on the top, I have 5 times 1, 3 times 2, 5 and 6, and I add them. That'd be 11 tenths. Done. Okay. Extend that to this. 1 plus tangent of x. What in the heck? That's not even close to the same thing. Or is it? What's tangent really equal to? So if this was too much for you, write this instead. Do they have a common denominator? What's the denominator on the 1? Yep. Do they have a common denominator right now? No. How do you get them to have a common denominator? You multiply by something on the top and the bottom. What do I multiply by here? Cosine of x over cosine of x. All right. We're getting somewhere now. Finish it. I'll be kind of thinking you're slacking unless you took at least 3 pages of notes today, because there's so much stuff to write. All right, so, and the denominator was cosine x, and on top we have cosine x plus sine x. All we did was add 2 fractions together. And I know you might be thinking, was that simplified enough? That's not the point. This would just be one little part of the problem. Remember, the problem was 1 plus tangent x. We could change that into this. Why would that ever be good? Because maybe the rest of the problem that I didn't show you was that you were supposed to multiply it by cosine x. Do you get how if I bring down that multiply by cosine x, these cosine x's would cancel then? I'm just saying that you may not even see why you need to add them together. But if you ever have 2 things that are fractions, like 1 over 2 plus cosecant of x, if you need to simplify it more because it's in the middle of a big problem, and maybe the rest of the big problem is it's all over, let me think, sine of x. If you're in this problem with a big fraction and I got a fraction on the top part too, make that have a common denominator, add it together, then you can do the flip and multiply thing with fractions. All right, so one little step at a time. Take the part I put a box around, make it have a common denominator. So cosecant, 1 over sine. Do they have a common denominator? No. So I multiply this one by sine x and sine x. Are they still going to have a common denominator now? No. What do I have to do the other one to make it have a common denominator? Multiply it by, if I multiply the bottom by 2, that helps, but then I have to multiply the top by 2 also, right? Because these parts that you multiply by have to be equal to 1. So now on top part of my big problem, I have sine x plus 2 over 2 sine x. And on the bottom part, I still have a divided by sine x. Fractions play nice with other fractions. Wouldn't it be nice if that sine x was a fraction too? It actually would be, because then you'll see that you have a fraction over a fraction, and that's on my basic sheet too, because you got to know how to flip and multiply from the bottom. Remember that? So now I'm going to move this up to the top, flip and multiply. Change it to a multiply problem instead of a divide. Multiply by 1 over sine x. All right. Now, this one didn't simplify down the way I thought it was going to, but at least you've got the main idea of how to find a common denominator. Now, let's do one off your homework. Oh, wait, I'm not quite ready to do your homework. I know you may not be like understanding exactly how this one finishes, and that's okay. It'd take me too long to finish it, and it's not going to work out really pretty anyways. So let's go on to the last thing I have to teach you, and that's called cofunctions. Okay, do you remember that sheet of identities I gave you yesterday? And I thought it was all you'd need for the next few days. There's one more kind. Let's make sure you know what the first few were called. The very first ones I gave you were called the reciprocals. Do you have those listed? Those are the ones like sine is equal to 1 over cosecant, like that. I'm talking about? That was the reciprocals. Make sure you have those. The next one is the odd evens. They're not necessarily next in order, but the odd even ones were the ones that were like sine of negative x is equal to negative sine of x. Those were called the odd evens. The Pythagoreans were things like sine squared plus cosine squared is equal to 1. Those are called Pythagoreans. The quotient ones were called, the ones called quotients are tangent is equal to sine over cosine, and cotangent is equal to cosine over sine. All right, have all those? All right, make one more section, and it's called cofunctions. There's things that go together. Peanut butter and chocolate, they go together well. Then there's some things that kind of logically go together. I'll say a word and think the word that goes together with it in your head. Pilot and what? Plane. No, plane. That's good. Okay. Co-pilot, and that's what I was thinking of. Very good. Pilot and co-pilot. Okay. How about this one? Batman and. All right. Good. How about crate and barrel? Very good. Mostly it was girls saying that answer, but anyway. So, Navy and, okay, I could be by Army. Navy, SEAL, okay, good. I was thinking you were thinking SEALs. All right, good. So now, cofunctions, things that go together. Sine and cosine, very good. Sine and cosine are cofunctions. A lot of people don't even know that if you write them all the way out, S-I-N-E, there's an E on the end of that. Did you know that? The only reason we say S-I-N is because it's short. It's a three-letter combo. It's like tangent is really T-A-N on the calculator, but it's tangent is the whole word. Well, sine is S-I-N-E. What goes with that? Cosine. They are called cofunctions. They kind of like, if you were a co-captain of the team, it's like people that go together. All right, so this sine and cosine go together. So I'm going to show you something that you probably never knew. If you had sine of 30, that's exactly the same as if you have cosine of 60. So in other words, on the calculator, if you were to type in sine of 30, it gives you remember this one yet? 1/2. Memorize it. What did I just say then? What will cosine of 60 be? 1/2. All right. Let's say you wanted to find sine of 10 degrees without using the sine button. What could you do? Cosine of 80. Very good. Why? Because these two add up to what? All right. So let's say we had sine of 5 degrees. That would be the same as cosine of 85. Has to add up to 90. That make sense? Okay. So then what can you tell me about tangent? Take a wild guess. Tangent of 30 would be same as what? Cotangent. That's the one that goes with tangent. Cotangent. See, it's a cofunction. Tangent of 30 is cotangent of 60. Let's go the other way, because you know how the calculator has a tangent button. It doesn't have a cotangent button, does it? So what if you wanted to find cotangent of 45? That'd be the same exact thing as tangent of 45. That one's tougher to check on a calculator because you can't do cotangent on the calculator directly. But it would work because these two add up to 90. How about this one? Cotangent of 81 degrees would be the same as what? Tangent of 9 degrees. These add up to 90. You getting this? So extend it one last time. What are the last two I haven't done yet? Yes. Secant and cosecant. Those are cofunctions. We usually abbreviate them with SEC and CSC. So secant of, let's say, 70 would equal cosecant of what? Still adds up to 90. You getting this? All right, so here's how you actually would want to have them on your sheet. What I was writing before is all okay to have on your sheet. But the way you're going to see them the most often is like this. See if anybody can make this leap. If I use cosine of theta, what's that equal to? Sine of 90 minus theta, but we don't use 90 because we're in trig. We use pi over 2 minus theta. Very good. That's it. And by the way, the sine and the cosine are interchangeable. So you could start with sine, you could start with cosine. Doesn't matter. So in other words, I could say sine of theta equals cosine of pi over 2 minus theta. It's supposed to be a theta. Okay, and if you get that, then it should be a fairly short leap to get to here. Tangent of theta would be equal to what? Cotangent of what? Pi over 2, which is the same as 90, and then what? Minus theta. There you go. They are written exactly the way you see them on the board. So if you're asking, will it ever be 90 degrees? No, it will never be 90 degrees. This will always be in radians. It's irrelevant on, like, the theta can be anything you want it to be. It's an angle. It could be any angle. It could be in degrees or radians. Doesn't matter. But the way we're going to write it always uses a pi over 2. So I guess you could say it's always written in radians. See, you're not going to use it that way. Here's how you're going to use it. Let's say we had a big fraction problem where we had tangent theta on the bottom. And on the top, we had cotangent of pi over 2 minus theta. Do you get how you can pull things out, pull this out, and put something back in? So I'm going to pull out this complicated looking thing. What am I going to put there? Tangent of what? So you get how it's tangent of theta over tangent of theta then? So what's the answer equal to? 1. So it's not like you're going to be figuring out angles with this. You're going to be using it to cancel other stuff. Because this got replaced with tangent of theta. And then tangent of theta over tangent of theta equals 1. I'll give you another one like that. See if you can handle this one. It wasn't a proof. Okay, sine of theta is equal. Let me think. I'm going to multiply that by cosine of pi over 2 minus theta all over sine of pi over 2 minus theta. Whew, intense. There's a typical question that involves cofunctions. So your first job is to figure out, do you recognize any of those, like off the sheet? This is the one I'd hone in on. And what does that turn into? Okay. So that's sine theta on top, along with another sine theta. It'd be nice if those had canceled, but they're not gonna. So this one right here turns into a sine theta. So you have a sine theta times a sine theta. What does that make? Not 2 sine theta. Sine theta times sine theta. Sine squared theta. How about on the bottom? What's that? That's cosine of theta. And I'm getting too much to try to keep in my head, so I'm going to rewrite it down here. Sine theta times sine theta over cosine theta. Now you could go 2 different ways here. You could say sine squared over cosine. That doesn't really get me anywhere. But what's sine theta over cosine theta? Tangent theta. So then I could say this is really sine theta times, what did this turn into again? Tangent theta. And that's it. Good enough. I know it's hard for you guys to tell if you're done or not. A lot of times you end up with just one function at the end, like sine. If you end up with just one function, you're definitely done. If you end up with a function like +1, definitely done. If you end up with just a number like 1, definitely done. This one, I would have also been thinking, could I change the tangent into something to make that sine cancel it? But it doesn't. The tangent turns into sine over cosine, and then the sine won't cancel. So this would be an okay answer. Good enough. All right. Let's go a little further. There's one other concept that you have to be able to handle, and that is when you are, let's see, factoring out, so I'm going to pause for a second. Okay, so I wanted to make sure that you knew how to handle this situation. Sine squared theta over sine theta. You know, it's a lot like having x squared over x. Do you get that they can kind of cancel each other? So that sine squared theta is really like sine theta times sine theta. And then I could just go cancel, cancel, and the answer is sine theta. I'll show you another one like that. Cosecant squared theta over, let me think. Oh, let's just make it cosecant. That'll be simple. Can I do some canceling here? What's the final answer? cosecant. All right. Another topic. I think we'll just run into it when we hit some problems on the worksheet. So I'm going to hand these out. Hold on just a sec. Okay, let's do number 1 off the worksheet together here. 5.1, worksheet number 2. This is problem number 1. Do you remember a little snappy saying about the one with the tan? The one with the tan is what we seek. All right, so cosine, the first problem says this. And yes, there's other ways to say that, and you're welcome to say it how you want to say it, as long as you keep it clean. This one with the tan, I would change that into secant. So that's going to be a secant squared. Remember, that only works in things that are squared. This cosine x part. Remember what I told you about moving everything towards something? What did I say about that? Cosine and sine. Move everything towards cosine and sine. So that cosine is already a cosine. It's probably not going to be any simpler if I make it 1 over secant. Although, wait a minute. If I make it 1 over secant, this is one of those times when it's actually going to be smarter not to move everything towards sine and cosine. I do want to remind you that often works. But in this case, I should take this cosine and turn it into a 1 over secant. Can you see why? Because then I have a secant squared over a secant, and we just handled that 2 seconds ago. Now we have secant squared over secant, and now that simplifies. Cancel this, cancel that, and it's secant x. And this was a proof, so I just have to bring this all the way down and say equals secant x. There we go. That was number 1. Okay, number 2. Ooh, it's got a cofunction in it. I'll write it down while you try to solve it. You're using a y. Yeah, it's okay. You can use y's or thetas or x's, doesn't matter. Secant y times sine of pi over 2 minus y equals 1. All right. First thought, that's a cofunction, just saying, please simplify me. Cosine of what? Very good. Times secant of y? How's that going to help? What did Mrs. Server say again about generally you want to kind of move it towards what? Sine and cosine. Okay, so then secant could be what? 1 over cosine times cosine. And I'm going to put that over 1. And then the cosines will cancel, and I get a 1 equals a 1. And if you don't finish like that, you have not proved. You haven't have your final proof statement. You need this. Okay, let's look down at number 8. Number 8. Ooh, I see a 1 with the coat. What is a 1 with the coat? Cozy, very good. So on number 8, replace the 1 with the coat as a cozy. Remember, it's CSC squared. So on top, on number 8, you've got cotangent squared. On the bottom, we just replaced 1 plus cotangent squared with secant. Or, yeah, no. Pause for a second. Okay, so cotangent x over, and 1 plus cotangent can be replaced with the 1 with the coat is cozy. And if you're a rookie at this, you might be saying, how does that even help? But if you're experienced at this, you know you got it down to 2 functions. And that means you're probably going to be able to do some more canceling in just a second as soon as you replace cotangent with... What are we supposed to generally move towards again? Sine over cosine. So therefore cotangent is cosine over sine. This part right here turns into cosine over sine, and they're squared, over, what are we generally supposed to move cosecant towards? Sine and cosine. What is cosecant? 1 over sine squared that was this part right here turning into this part. And then, once again, on the top 20 important skills I had, this thing, fraction over a fraction. We don't really need a common denominator because we're multiplying. So we do need to handle, instead of dividing by that, we can multiply by, flip it, sine squared x over 1. And why is that good? Cancels. This was a moving up here, right? So it's changing it to a multiply by the thing flipped. All right. Here's my problem now, and now this cancels this. I'm down to just cosine squared. Now I know some of you are like, so do you go further? Well, what are the options? Was cosines 1 over what? Secant. Would that actually be any simpler than what we already have? No. If you get it down to one function, you're done. Even if it's squared. Now, there's an important caveat to that. You have to know how to handle it if they need you to replace that with something else. Like if we were in the middle of a problem and I needed to replace cosine squared with something else. Do you get that there's a statement about cosine squared? There's not many, but there's one. Nope. Yeah, that's the one with the code is cozy. That's different. Cozy is CSC. Okay. What's the one that has cosine squared in it? There's only one. Other than 1 over secant. That's so cosine squared plus sine squared equals 1. So what is cosine equal to? That's like giving you this. This is a fact. You can count on it as a fact from now on. It's a given. It's an identity. And then I can solve it. I can solve it for cosine squared. I can get this alone. So I can go minus sine squared x, minus sine squared x. And now what's cosine squared equal to? 1 minus sine squared. Now, do I think it's any better to write that? No. But what if we were in the middle of a problem and the bottom of the fraction was 1 minus sine squared? The better answer is the simpler answer. Cosine squared x is simplest. What I'm trying to say is, let's say the problem was like this. You have to be able to go, oh, I could replace cosine squared with something. You pull up in your memory banks, you pull up the identity that you know is true. Cosine squared x plus sine squared x is equal to 1. And then you solve it for cosine. Solve it for cosine. Minus sine squared x. Minus sine squared x. And then that cancels that. And then I have cosine squared x is equal to 1 minus sine squared x. Do you get how I just solved that little thing? And now I know that cosine squared can be replaced with 1 minus sine squared. So this top right here can become 1 minus sine squared. And why is that good? Because this can cancel this. Then the answer is equal to 1. Let me give you another one like that. Try it. Now, by giving you a lot of help like this, I'm also burning through a lot of time. Try this one. I'm telling you, I'm doing these things because I know they're good for you. I know it's going to help you. But I am going to cut some of your problems off your worksheet and acknowledging the fact I'm not giving you too much time to work in class. What? Nope, thank you, but it's okay. All right, so the tangent squared, I'm going to cross off tangent squared and replace it with, well, if you don't know, you go off to the side and you say, the one with the tan is what we seek. And so if I want to know what tangent squared is, I got to solve for tangent squared. So I got to take away 1 on both sides, and now tangent squared's alone, and it's secant squared minus 1. Now, this might mess with your head. Secant squared minus 1 over 1 minus secant squared is not the same thing, is it? So can you cancel them or not? No, you can't cancel them the way they are. Now, could I factor out a -1 from this? And let me just see what happens if I do. If I factor out a -1, then would I have negative secant squared x plus 1? Do you get what I just did there? I took the top and I factored out a -1. And now I'm going to take the top and I'm going to rearrange it. Can't these guys switch places? 1 minus secant squared x. And now on the top I have that. And on the bottom I have that. And I can cancel. And the answer is -1. That was a great scared look. That was awesome. So if I wanted to sum that up in one snappy statement, x minus 1 over 1 minus x, they can't cancel just as simple as just cancel, cancel. But they can cancel and give you an answer of not 1, but -1. All right. Okay, now let's look at your homework and may go toss a couple out that we don't need to do. That's all I have for the video for today.